This is the full section of chapter 1, circular motion, and this section is about objects moving in vertical circles. So what we mean by objects moving in vertical circles is that we see a circular path like this, and imagine this is the view you see from the front. So imagine maybe like a pendulum swinging around like this, and you push it with enough force that it maybe goes around to the top and it carries on moving around like this. So this is the front view of this object moving in this vertical circular path. Now there's one of three things that this could be. It could be a particle attached to the end of a light rod. So imagine like a rod here, for example, and you've got a particle on the end. The rod would be rigid, it's light, so ignore its mass. You've got a particle on the end here, and it's allowed to swing freely, and if it's given enough force, then it will continue to rotate around this circle here in this circular path. It could be a small bead threaded on circular wire. So the blue circle here represents some wire. There wouldn't be a rod in this case. That purple line would have represented the radius. And so we've got a bead threaded onto this wire, small bead, and this wire, again, pushed with enough force, will go in this circular path. So bead threaded on circular wire. Or it could be a particle attached to light inextensible string. Let's put that on there. So it's going to be similar looking to the first diagram that we had. So there's our string there, and particle on the end, and again, push with enough force, it's going to go around in this circular path. So let's go back to our diagram here. So we'll label this point here the center of the circle O, and the point where the particle is, we'll label that P. We're going to be interested in the radius of this circular path here, so we'll just label that as R here, basically the radius of the circular path. And since this is a vertical path, we're going to have gravity acting downwards like this. And just like before, we're also going to have acceleration acting towards the center of the circular path. So that's going to be either radius times by omega squared, where omega is the angular speed, or that acceleration acting towards the center as v squared over r, where v is the linear speed, or question may just say speed. Now we're going to be using the work energy principle to help us answer questions of this type. That is that the kinetic energy and the potential energy remains constant, because we're not going to be considering problems where there is work done against friction. So no energy is going to be lost in these types of questions. So we can just assume wherever point we are in the circular path, the sum of the kinetic energy and potential energy is going to be the same. It's going to be constant wherever we are. Now, when we're doing these types of questions, we should take the lowest point of the circular path, that is the bottom of the circular path, as zero potential energy. So potential energy equals zero. And the last thing is, sometimes we're asked if an object's going to perform a full circle, or maybe the velocity, minimum velocity we need for a full circle, or minimum tension. Well, it all depends what type of thing we have here. So if it's a particle attached to the end of a light rod, if it's going to perform a full circle, then the speed at the top, when it gets to the top here, needs to be greater than zero. So it's just got enough to carry on going round. If it's less than zero, when it gets to the top, it's going to sort of flop back down in the direction it came from. If it's a small bead threaded on circular wire, again, the speed of that bead as it gets to the top of the circle needs to be greater than zero, so it carries on moving. However, if it's a particle attached to a light inextensible string, then the tension at the top needs to be greater than zero. Otherwise, what will happen, it will get to the top. There won't be enough tension to let the bead carry on, or the particle carry on, and it was just going to go loose. Yeah, so for that one, it's slightly different, but in all three, we've got this condition where something needs to be greater than zero, either the speed or the tension. Example 16. A particle of mass 0.4 kg is attached to one end A of a light rod AB of length 0.3 meters. The rod is free to rotate in a vertical plane about B. The particle is held at rest with AB horizontal. The particle is released, and there's a couple of things here we need to calculate. So the first thing that we need to do is to start with a diagram. So we'll have our circular path like this. We've got the center of the circle, which is actually B, because it says that the object is attached to the other end of the rod at A. So we'll just mark this down as A here, and it's released from rest. So at this point, the linear speed is 0. So we'll just put 0 here. And it says it's released from rest, so we know that it's going to rotate in this direction here. And in part A, we need to find the speed of the particle when it gets to its lowest point. So the lowest point is going to be down here. So we want to work out what this speed is here, linear speed. So we'll call that V. And we'll also remember that at the bottom part here, this is going to be 0 potential energy. So we take the lowest point as 0 potential energy. Right, so there's going to be no energy loss because there's no work done against friction. So the kinetic energy and the potential energy is going to be constant. So Ke plus Pe equals constant. So what we'll do, we'll work out the Ke and Pe at the start. So kinetic energy, it's released from rest, so the kinetic energy is 0. And the potential energy at the start, that's going to be mgh. Now, since this is 0.3, I should put that on there. We're told that it's 0.3. Then it's at a height of 0.3 meters above this 0 potential energy. So this is 0.3 meters above this point here. So potential energy is going to be m 0.4 g times by h, which is 0.3. So that is 0.12 g. 0.12 g. Okay, so let's now work out the potential energy at the bottom, or the lowest point. I'll just call it the bottom here. So the kinetic energy is going to be half m 0.4 v squared. So v squared is what I want to work out. And the potential energy is going to be 0 because we're taking that lowest point as 0 potential energy. So since these remain constant, the total energy at the start, which is going to be 0.12 g, is equal to the total energy at the end, which is going to be half times 0.4 or 0.2 v squared. So from there we can work out v squared. So that will be 0.12 g divided by 0.2. So we can square root that to work out v. So we'll just put that down. Now we could leave our answer, I suppose, like this, or we could tidy it up a bit in terms of g, or we could write it to 2 or 3 significant figures. So to 3 significant figures, that would be 2.42 meters per second. So I'll just write 3 significant figures for this, and that's because we are using g. So don't give exact answers, give answers to 2 or 3 significant figures, or in terms of g. Okay, part B says the tension in the rod at this point, so that's down here. Now the tension is going to be acting towards the center. Then we've got the weight of the particle, 0.4 g, acting outwards. Now remember, the acceleration acts towards the center. So we're going to use F equals ma. Right, so since it's acting towards the centre, we resolve towards the centre. Let's just mark this as T here as our tension. So tension is going up minus the 0.4 G going down, and that's going to equal M, 0.4 times A. Now, that's going to be the acceleration, and since we've got the linear speed, we're going to be using v squared over r to find our acceleration, and we have v squared is here. Now I could write this here a little bit more simply as 0.6 g, which I will do. So there's my v squared, 0.6 g divided by the radius, which is 0.3. So a little bit of rearranging, I can find t. So that will be 0.4 times 0.6 g over 0.3, I suppose, which is 2g. I suppose put 2g, and then I'm going to add 0.4 g to get t. Now that gives me exactly 11.76, but we need answers to 2 or 3 significant figures. So I will do 3 significant figures and do 11 point, that will round to 11.8 newtons. You could do 2 significant figures and give your answer as 12 newtons. So I'll just put at the end here that this is 3 SF. Example 17. A particle of mass 0.4 kg is attached to one end A of a light rod AB of length 0.3 meters. The rod is free to rotate in a vertical plane about B. The rod is hanging vertically with A below B when the particle is set in motion with a horizontal speed of u. So let's start with our diagram. So here's my circular path here, center of the circle, which is labeled as B. Then I have this light rod here with the particle attached at the other end, and this is the point A. We're told that the length of the rod is 0.3, so that's the radius of the circle, 0.3 meters, and it's set in motion, we're told, with a horizontal speed of u, so we're going to call that u here. And then in part A, what we need to do is to find an expression for the speed of the particle when the rod is at an angle theta to the downward vertical through B. Okay, so this angle is making an angle of theta with this line here. So let's put something like this and show where it's going. So this is where basically A is going to end up here. The angle here is theta. The length of the rod hasn't changed, so this is still 0.3 meters here. And we want to work out what is the speed of A at this point, which we're going to call V. Now remember, the speed is always tangential, or always a tangent to this circular path. So just like before, we're going to take the lowest point of the circle here, where potential energy is 0 PE. So let's work out the energy at the start. So that's going to be at the bottom. My kinetic energy is going to be half m times by the speed squared, which is u squared. So I can simplify that to 0.2 u squared. And the potential energy at that point is going to be 0. Let's look at the potential energy at the finish. Now what I mean by the finish is where it is at this point here. So the kinetic energy is going to be half m v squared, which I can simplify to 0.2 v squared. And then for the potential energy at this point, I need to work out how much higher this is vertically from this point. So it might be helpful if I drew a dotted line like that. I need to work out this height change. What is the length of this? Now we can use a bit of trigonometry because it's going to be 0.3 minus this length at the top here. So this length I need to subtract from 0.3. Now I can find this length by doing 0.3 cos theta. So this little length here at the bottom is going to be 0.3 minus 0.3 cos theta. So now we can do our potential energy. So that is m g h, and that height is 0.3 minus the little bit above it that I put that orange squiggly line on, which is 0.3 cos theta. So no energy is lost. We can use conservation of energy. So the total energy before, which is 0.2 u squared, is going to equal the total energy after, which is 0.2 v squared plus 0.4 g times by 0.3 minus 0.3 cos theta. And then the rest of this is just rearranging it to make v the subject. So we can write this as 0.2 v squared is going to be equal to 0.2 u squared minus 0.4 g times by 0.3 minus 0.3 cos theta. Now what we'll do is we'll take this 0.3 out as a factor, so you can think of this as 0.4 g times by 0.3. So then we'll end up with 1 minus cos theta, and then we're also going to times both sides by 5. So if we do that, we'll get v squared equals u squared. And as I said, we're taking out the 0.3 as a factor, so 0.4 times by 0.3 is going to be 0.12 g, and then we times that by 5. So that will become 0.6, so minus 0.6 g, then in the brackets 1 minus cos theta. The last step is just to square root both sides. So v is going to equal square root, it's got to be the positive square root, of u squared minus 0.6 g 1 minus cos theta. And we'll just highlight that before we move on to part B. And we'll just close that bracket as well. So part B is saying the minimum value for u for which the particle will perform a complete circle. Now remember, these particles, objects, perform complete circles when the velocity at the top is greater than 0. Now in this case, when we get to the top, at the top of the circular path, theta is going to equal 180 degrees. Basically it's like done a half turn to get to the top, so we're talking about this point here. So yeah, that means our theta is going to be 180. Right, so that means that this value of v here needs to be greater than 0 when theta is 180. So let's write that down. So square root of u squared minus 0.6 g 1 minus cos 180 needs to be greater than 0. Now cos 180 is minus 1. So we'll have here, let's just write that down. That's going to be minus 1. So we end up with 1 minus minus 1. So we end up with 2 in the brackets. So what we effectively got next is that u squared minus 0.6 g times by 2 needs to be greater than 0. And we can simplify that and say that square root of u squared minus 1.2g needs to be greater than 0. Now we need to rearrange this, so we've got u, so we can square both sides, so we'll have u squared minus 1.2g is greater than 0, so basically we'll end up with no square root here. Then we'll move the 1.2g across, so we'll have u squared is greater than 1.2g, and so u needs to be greater than or equal to greater than square root of 1.2g. So there we go. That needs to be the minimum value of u for which the particle will perform a complete circle. When u is greater than this value, that means that when it gets to the top, that velocity will be greater than 0. It will carry on and perform a complete circle. Example 18. A particle A of mass 0.4 kg is attached to one end of a light inextensible string of length 0.3 meters. The other end of the string is attached to a fixed point B. The particle is hanging in equilibrium when it is set in motion with a horizontal speed of u. So diagram again, and it seems we've got the same values as before. So we've got the same circle and mass. Now it doesn't tell us the position of the particle, but the fact that it's in equilibrium must mean that the particle is hanging vertically below A. That's going to be an equilibrium position. It's set in motion with a speed of u, so we'll put that on our diagram here, and the length of the string is 0.3 meters. Now with this question in part A, what we need to do is find an expression for the tension in the string in terms of u when it is at an angle theta to the downward vertical through beam. Okay, so we've got our particle in this type of position here, so it's now moved around to A, and we've got the string, and we want to find an expression for the tension. So that acts towards the center, as does the acceleration. But we also have the weight of the particle acting downwards. It's always going to be acting downwards, and that's going to be 0.4g. Now we're going to have to resolve in a particular direction, either up, down, or towards the center. Now the acceleration is acting towards the center, so is the tension, so it makes sense to resolve in this direction, which means we need to work out a component of the weight. So we need to work out this component here. I'll draw in the other one just for reference, but this is the actual one that we're going to be using in our F equals ma equation. Now if we put on the angle at the center, now that was theta. This angle is also going to be theta. This is sort of corresponding angles, I think. So these two are parallel, and we've got corresponding angles. So this angle is also theta. So this component that I'm interested in here is going to be 0.4g cos theta. So resolving towards the center, we're going to have t minus 0.4g cos theta equals ma, so 0.4 times by a, which is going to be v squared over r. Now v squared is going to be the velocity at this point, so we'll put that on. So we'll call this one v, and our r is 0.3, so we'll write this as t equals 0.4 times v squared over r, 0.3, plus 0.4g cos theta. Now you'll notice the question said that we need to give our answer in terms of u. We've got an equation in terms of v, so this is now where we're going to be using the conservation of energy to get another equation where we can substitute our v for u. So we'll start at the bottom, at the start here. So I'll put start, you can put bottom if you want to, or lowest point. And we're going to have zero kinetic potential energy, as we said before. So PE equals 0. And the kinetic energy is going to be half mv squared, or u squared in this case. So half times 0.4 times by u squared, and we'll simplify that as 0.2 u squared. So now the total energy, or the energy at this point here, where it's at an angle of theta. So I'll just put, you could put end or finish, or when it's at the angle of theta. Just make it clear, you know, which point you're talking about. And at this point, the potential energy is m times by g times by h. So that's that height increase. Now remember, we did this in the previous question, but I'll mark it on again. We want to find out what this distance is here, and it's 0.3 minus 0.3 cos theta. So I'll just put that down. 0.3 minus 0.3 cos theta. Right, so the total energy at the lowest point, which was 0.2 u squared, is equal to the total energy at this point at an angle, which is 0.4 g times by 0.3 minus 0.3 cos theta, plus the kinetic energy at this point, which I haven't done yet. I should put that now. So the kinetic energy at that point is going to be half mv squared. So half m is 0.2 v squared. Almost left that out. So this is going to be the total energy at the end here, or at this point when it's at an angle. So put 0.2 v squared. So the rest of this is now going to be making v the subject, so I can substitute an expression for v here. Now if we rearrange this, and you may remember from the previous example, we got v equals square root u squared minus 0.4 g times by 1 minus cos theta. That was the answer from part A from the previous example. So we want v squared because that's the substitution we want to make. We want this in terms of u. So v squared is just going to be that previous answer squared, which is just going to be u squared minus 0.6 g times by 1 minus cos theta. So that can just be placed here. Now we've got 0.4 divided by 0.3, which is 4/3. So we can write our answer as the tension equals 4/3 of v squared, which is u squared minus 0.6 g times by 1 minus cos theta. Okay, so that would be our answer. We could multiply that out if we want to, or just leave it as it is. And last of all, part B. And part B is asking us to find the minimum value for u for which the particle will perform a complete circle. Now right at the start I said that if you have particles attached to string, then we want the tension at the top here to be greater than 0. So when theta equals 180, we'll write that down. So when theta equals 180 degrees, we want t to be greater than 0. So we have an expression for t here. We want all of this to be greater than 0, and we'll put 180 here for theta. So that'll give us -1. So we're going to end up in this bracket with a value of 2, 1 minus 1 minus 1. So effectively, when theta is 180, this last part of the expression here is going to be 1.2 g. So we'll just save a bit of time and write that down. So we want 4/3 times by u squared minus 1.2g to be greater than 0. That means that we want u squared to minus 1.2g is greater than 0. Then I'll move the 1.2g across to say that I want u squared greater than 1.2g, and then from there I can square both sides, square root both sides. So I want u to be greater than the square root of 1.2g. So we'll just highlight that as our final answer. So you should now be able to do exercise 1D on pages 23 to 25 of the textbook.